Let's take a look at 8.5, which is on partial fractions. So basically, using the concept of partial fraction decomposition, we will be able to simplify the integrand and evaluate more easily. This comes up periodically throughout the rest of Calc, obviously this chapter, but throughout Calc, but also if you're moving on to engineering and stuff, you'll see it in higher levels as well. Differential equations, for example. It's not used a lot, but we definitely need to cover it so you can see how to use it. So you may or may not remember partial fraction decomposition. It is done in college algebra and I believe in high school algebras. But I think when I took it, I don't remember doing it. So I want to make sure we know how to do these. So first, let's go over just adding rational expressions. Again, right, this is something you should know. So suppose you have, and I went ahead and wrote this up because this is just a lot of stuff ahead of time. So you can do this piece by piece if you want. Suppose you have this question to just add it. So you're just adding the rational expressions. And so to do that, you get an LCD, which is that denominator, multiply both by what's missing, top and bottom. And you get, of course, this LCD. And so the 2 gets the x plus 2, and the 4 minus x gets the other one down here, x minus 3, which is here. And then you, of course, add it up. You multiply all this out, distribute the negative, etc., all the way down to here. And so the question is really, what if you're given this form? How can you go to this form? So we essentially want to go from here back to here. If you were to integrate this one, you can use, this will be a natural log, and this you can again separate out and divide it even further, which we'll talk about later. So let's go over partial fractions. All right. So let r of x, capital R of x, equal f of x over g of x. So be a rational function with degree f of x less than, so this has to be true, less than the degree of g of x. And so what you can basically do, and this part is just more of the conceptual theory part, but you end up with f of x over g of x equals, and then you're essentially doing this. You're simplifying, you're breaking it down into that form. Okay, so what you get then is this fraction plus this fraction plus etc. all the way down to f sub r. And so each of the f sub k's would look like this. So you end up with a over ax plus b to the n, or you end up with ax plus b, and those capital A and b are constants, over ax squared plus bx plus c to the n. So, and I'll get to this in a second, but in this case, it's an irreducible quadratic over the reals, and this is like a linear factor. Right? So this is a linear factor to a power, and this is irreducible quadratic over the reals. Well, I think I define that later. So then you have two rules. Call it whatever you want. They're not really properties. It's procedure 1, procedure 2, rule 1, rule 2, whatever. So rule 1. Rule 1. You have the denominator of the form ax plus b to the n, and then n is greater than or equal to 1. If you have that form, then your partial fractions look like this. You have a1, so this is how you would break it down. a1 and then ax plus b plus a2 ax plus b quantity squared plus a sub n ax plus b to the n. So in other words, you're taking that ax plus b and you need a constant for each power. So for 1, power of 2, all the way to the power of n. In practice, we won't really do more than a couple, but that's what happens. Okay, and I think I won't. Here's my example we're going to try. I'll do that later. It's all written up for you. Rule 2 is that irreducible quadratic. So the denominator is the form ax squared plus bx plus c to the n is irreducible over R, meaning the solutions would be complex, right? Like if you solve that or try to factor it, you'd have complex solutions. So that's what we're talking about. So that's a little more complicated. So, excuse me. So what you end up having is you have to write a1x plus b over ax squared plus bx plus c. And then you do the same process for each one. Then you have a 2x plus b2. So for each power, you need a factor. And then you get ax squared plus bx plus c squared, etc. Plus all the way down to a sub n x plus b sub n over ax squared plus bx plus c to the n. So that's what happens if it's irreducible. So here's the thing though, for each of the denominators, that's what we will do. We will write it in, so like this form. So I'll show you in a second here, but if you have x plus 1, then you do one of these. But then if you have a different factor, you do the same thing. You expand it out. So it's easiest just to show you, of course. So let's take a look. I'll go ahead and bring this up. Okay, so let's look at this example. Oops, and I was going to make that the same font size. Or thickness, I guess. Okay, so so evaluate that, and you have that this degree is 1 less than this degree. Okay, and that's good enough. So 1 1, we have degree F is less than degree G, so check. Okay, then 2, you need to make sure the denominator is factors, so factored. So factor g of x, and so you have x cubed plus 2x squared minus 3x equal to x times, so you just factor out the x obviously, so x, and then it's x squared plus 2x minus 3, and then it's x times x plus 3, x minus 1. All right, so now, so what you do is you do all this work ahead of time before you try to evaluate that. Remember, our goal is to evaluate this thing. So first we want to factor and do the partial fraction decomposition, and then we will integrate. So we want to take this integrand here and write it in the factored form. So this equals the 4x squared plus 13x minus 9 over, and then factor it. Right? Then we're going to do this factorization just like we had here. So now we do the expansion. We're going to say that's equal to, now, so look what you have. You have each of these are linear factors. So when you go back up to our process here, all you have is one of those per factor. So it's just this for this one, and then you'd put in maybe a B for this one and a C for this one. It is just this form. So you write A over X plus B over X plus 3 plus C over X minus 1. Okay, so each factor, just to be clear on this, each factor is linear, and like with degree 1. So you're not going to write it again and square it or anything. So each factor is just that. So that makes this a lot easier. So now what you do, and what you really are considering and looking at, is this. So you look at this equation, and you want to basically solve for A, B, and C. And there's a couple ways to do that. We'll show you a couple here. So the first thing you do is, so you take this and you multiply on both sides by the LCD. Okay, so when you do that, left-hand side is just 4x squared plus 13x minus 9. Right-hand side, each one of those factors will reduce. So you get, so let's do that. So the LCD, you don't have to write this down, but the LCD is x plus 3, x minus 1. So then you get 4x squared plus 13x minus 9 equal to A. So you have the A, and then but the x is gone, and you're left with x plus 3, x minus 1 plus b times x, and then what's left? X minus 1, and then c times x. Usually I don't put a parenthesis around the x, but x plus 3, like that. So our goal is to find your A, B, and C. I said that. I'm going to write it down. Goal. So find or determine A, B, and C. So this is how you want to go about it. This is the easier way to do it. We're going to choose values for x that make each factor 0. That make each factor 0. And this is what I call method 1. And really you always do method 1 if you can, and then kind of a hybrid of method 2, which I'll show you. So method 1, that's what we're doing. So basically what I'm saying then is, if you look at you can look at the LCD really. So you're going to choose x to be 0, -3, and 1. And it doesn't have to be that order, but I think I did 0, 1, and -3. And then you substitute in and solve for the variable. So let's see. So first, let x equals 0. Then we get, okay, so put in 0, and right? So then gone, that's gone, and then you get 3 and a -1. So that'll allow us, check that out again, do it in your head, plug in 0, see what you get. You get -9 equal to a, and then that ends up being just -3. Okay, so that means a, if and only if, a is equal to 3. So that's, you found a is 3. Okay, then you're going to say x is another factor, 1. That makes it 0. So now you're plugging in 1 to everything. Do the easy ones first. You're putting in 1 to everything. It's going to 0 out this. That's going to go to 0. That's going to go to 0. And you'll be able to solve for C. So this is an easy case. This is what you can do when they're all linear factors like that. Okay, so when you do that, do this in your head, substitute in. You should get 4 plus, well, write it down too. 4 plus 13 minus 9 equal to C times 4. And I'll let you solve that. Add that up and divide, etc. You get C is equal to 2. Okay, and then do the next one. Let x equal -3. And then go ahead and do that. What do you get? Put in -3 everywhere. Now, if we put in -3, that's going to 0, and that's going to 0, and you'll be able to solve for B. Okay, so substitute in, and I'm not going to, you can write that down. So check it out. But you get B is equal to -1. All right, so this just allows us to do the partial fraction. Then we got to integrate. Well, that's a whole other thing. All right, so let's continue though. And make sure you check this on your own. Make sure you see that that's -1. So what we have then is that this, now we can break down the integral and plug it back in. So we have, let's go back up here. That's our whole problem. So we have that -1 is going to go here. we have 2 will go here. I'm not sure why I need to change colors on this, but 3 will go here. And we substitute back. It looks nicer, I guess, huh? So that's what we found by choosing those values. The order, of course, doesn't matter, but you will be solving for your A, B, and C. All right, so then, let's see. We don't need to rewrite this whole thing. Let's just put that into this form, which equals the integral of all that. So we're going to have this original question. I'll write it down over here. Put it over here. And then we're going to say that equals the integral of all of this up here. Okay, so that's all of that. But of course, that you could have written down right away if you wanted to. But now we know A, B, and C. We just found A, B, and C. So that's equal to the integral. I'll just come back here to the integral of, what was it, 3? So 3 over x. And let's just, right like that. Okay, so plus your b, which is -1. So we'll write that as a negative in front. So it's usually what you like to do. So -1 over x plus 3 plus 2 over x minus 1 dx. All right, so now do you recognize that integral? All of these are really nice integrals to do. Those end up being just natural logs. So this equals 3 ln absolute value of x minus ln absolute value of x plus 3 plus 2 ln absolute value of x minus 1 plus c. And you can actually simplify that a bit by using properties of logarithms and write natural log absolute value. I don't know why it does it on me. Absolute value of x cubed, bringing up that power, x minus 1 squared, again, bringing up the power, and then the negative brings the x plus 3 down, and then plus c. So bring up the power here, this negative, bring up that power, bring it down, or just minus divides by the what's inside. And then 2 again, bring it up. So you can combine your logarithm like that. Okay, let's talk about method 2 for solving. And you do need to know this method when things don't work out nicely. So what you do is, let's take this original expansion here. I'm circling it if you can't see that. So take that original expansion, and I didn't need that thing there. Okay, and then what you do is you expand. So you multiply everything out. And I'm going to kind of speed it up, but you expand that out, and what you'll get, well, actually, I guess I kind of do it. So this ends up being a x squared plus 2x minus 3, and then b times x squared minus x, plus c times x squared plus 3x. Okay, and then you distribute and collect like terms. Okay, and maybe I should write that down. Let me give myself some space. Okay, so distribute collect like terms. So this is still part of the expansion step, really. So when you do that, you get ax squared plus 2ax minus 3a plus bx squared minus bx plus cx squared plus 3cx. Okay, and then we collect like terms. So you have your ax squared and your bx and your cx. I like to highlight this sign as well. And then you have your linear terms like that. And then your one constant there. And so this equals, I'm going to go ahead and factor out the x squared in each of the ones in green there. And you get a plus b plus c x squared plus, and then similarly factor out the x in the yellow terms there. So it's 2a minus b plus 3cx minus 3a. And now what you do is equate coefficients. So we take the coefficients and we want to set this equal to 4. So 4 has to equal the coefficient of x squared. And then we take this, the coefficient of x, that must be 13. And then we take the negative 3a, that must be negative 9. Okay, so when you equate coefficients, you end up getting 4 equal to a plus b plus c. 13 equals 2a minus b plus 3c. And then negative 9 equals negative 3a. And what you have here is a linear system of equations. You have a linear system. And then you just solve the system. Solve the system. By substitution, elimination, or matrices. And I'm not going to do that. We already solved it. You will get the same stuff, but so you would solve that system. That is that's like the brute force way. That's just like not thinking about something and just doing it. That's not the preferable way. And there's a hybrid way of doing it. So this one will work because these were all linear. It's when you get the quadratic case that they don't always work. So kind of understand both. Equating coefficients is the concept comes up a bit. So understand that. And this would work. You can see right here what you get your A right away. So sometimes you choose values to simplify the system down in the beginning, but you still got to kind of equate coefficients at some point. Okay, we'll do one more. I don't want to make this way too long. We'll do one more using the quadratic factors case, and that'll be it.